In this video, I just want to go through a couple examples. So I'm actually going to give you the problem, and then I'm going to ask you to pause the video, work through it on your own, and then when you're ready, come back and check your work. So our first example, we're going to have 50 milliliters, so 50.00 of a 0.200 molar hydrofluoric acid solution, and it's titrated with a 0.100 molar sodium hydroxide solution. And we're going to calculate the pH. At the following points. So our first one, after 10.00 milliliters of base has been added, to halfway to the equivalence point, C at the equivalence point, and then D after 130.00 milliliters of our base has been added. So 4 different spots for you. Again, please give this a shot. Do note, I guess before I send you off, the concentration of my acid and base are different. So the volume to reach the equivalence point is not going to be the same, right? Remember, at the equivalence point, it's the moles of each or millimoles of each that are equal. You do need to calculate that volume, right? At the equivalence point, we are going to need to know the volume. I'm not giving it to you here, so you do need to calculate that. You need that so you can convert your number of millimoles to the correct concentration, right? Remember, we're going to take the millimoles that remain divided by the total volume, so you are going to need to calculate those numbers. We do need the Ka. So the Ka of hydrofluoric acid is 3.5 times 10 to the negative fourth. Alrighty, so give it a shot. When you're all set, hit play again. Alrighty, so hopefully you guys tried that. The first thing I'm going to do is I'm going to calculate my pKa. You didn't have to do that right away, but I know I'm going to need it. I'm going to use the Henderson-Hasselbach equation whenever I have a buffer solution. So I'm just going to calculate that now. I know that my pKa is going to be the negative log of my Ka. So negative log of that. And I get that my pKa is equal to 3.46. So I'm just going to put it in a box so I can find it easily later. I'm also going to calculate the volume that I need to get to the equivalence point. I know that we're going to need that number, so I'm just going to do that right away so I have it when we get there. So we're going to calculate the number of millimoles of acid that we have. So I have 50 milliliters. I have a 0.200 millimole per milliliter solution. So when I multiply those, milliliters are going to be canceling. And I'm going to end up with 10.0 millimoles of hydrofluoric acid. I know that at the equivalence point, I also need to have 10 millimoles of sodium hydroxide, right? Those numbers need to be equal at the equivalence point. That's our definition. I know that the concentration of sodium hydroxide that I have is 0.100, again, millimoles per milliliter, right? So my millimoles are going to cancel when I divide. So I'm actually going to need 100. I guess that's all I need for, I have 3 sig figs here. So I am going to have to write this in scientific notation. 1.00 times 10 to the second milliliters of sodium hydroxide. Right, just reviewing sig figs. If I was to just write 100, that's only one significant digit. Remember that these trailing zeros do not count. If I was to do something like this, I now have 4 significant digits. So the only way to get 3 is to actually write that in scientific notation. When I put it into my neutralization tables later, I might just leave it as 100, just noting that I do need 3 sig figs, and we'll have to fix that before we finish our problem. Okay, so part A. Anytime we're adding base to our acid, I'm always going to write that neutralization equation. I also need to figure out how many millimoles of base we have so we can plug those numbers into our change table. So I'm going to do that first. I have 10 milliliters of sodium hydroxide, right? That's just what is given in part A. My concentration of sodium hydroxide, 0.100 millimoles per milliliter. Milliliters cancel. And I have 1.00 millimoles of sodium hydroxide added at this point. And you could just write hydroxide. Sodium, again, is a spectator ion. So I'm going to then set up that table. I know that my hydrofluoric acid is going to react with the hydroxide ions from the base, right? Again, sodium is a spectator ion. I'm going to produce water, and then my salt would be sodium fluoride, but the sodium ions, again, are spectator ions, so they get canceled. So this is my net ionic equation. If you include sodium, that's fine. It's more accurate to include it this way because sodium ions are not undergoing a change. I'm going to then plug in those concentrations, the amounts, right? My number of millimoles. So if we go back up here, I have 10 millimoles of hydrofluoric acid, right? That's what's in our Erlenmeyer flask. We've added, at this point, 1 millimole of sodium hydroxide from our burette. We're going to subtract the smaller of the two from both. Add it to the other side. So when I subtract this one, I have 9.0 millimoles of hydrofluoric acid. All of my hydroxide ions have been neutralized, so that goes to 0, and I have 1.00 millimoles of my fluoride ions. So what I have is a buffer solution, right? Anytime I have my weak acid and its conjugate base, right, I have a buffer solution. So I'm going to use the Henderson-Hasselbach equation. Remember that we are plugging in concentration, so I do need to convert those millimoles to molar concentrations by dividing through by my total volume. So I'm going to do that first. So my concentration of hydrofluoric acid is going to be the 9 millimoles divided by my total volume. So again, going back up, we started out with 50 milliliters of hydrofluoric acid, right? That's what's in our Erlenmeyer flask. We've added 10 milliliters to it, right? 10 milliliters was added. So we have 60 milliliters total. So when we divide that out, I get 0.15 molar HF. And then we'll do the same process with my fluoride ions. I have 1 millimole. We're going to divide that by my total volume of 60 milliliters. And I get 0.0167 molar. Do watch out for your significant digits on these. I do have a different number for both my concentration of hydrofluoric acid and my fluoride ions. Right? If we look at these numbers, this has the 3 significant digits. If we go back up, right, I had 4, I had 3. When I multiply those, I get 3 significant digits. Here, this number also has 3 significant digits, right? This has 4, this has 3, so when I multiply it, I get 3. But now I'm subtracting, so here I have 1 after the decimal point, here I have 2 after the decimal point, so here I only have 1 after the decimal point. So 9.0 is correct for that. So 2 significant digits divided by 4 gives me 2 significant digits. If I look at this number, I have 0 plus 1.00, which gives me 1.00. So 3 significant digits divided by 4 gives me 3. So just do be careful on those. It can vary by number. So Henderson-Hasselbach, our pKa is up here. We put it in a box, we could find it, 3.46. Plus the log of my base component over my acid component. And then again, make sure you do that division before you take the log. And then I'm going to add that. And I get that my pH is 2.51. And again, I don't round after each step when I'm doing this on my calculator, so if you're coming up with something slightly different than me, that could be it. I am going to double check my number here real quick. And then I guess paying attention to significant digits again, when I divide these two, I'm actually getting 0.11. I'm keeping the whole number in my calculator, but from a sig fig standpoint, that's what I would have. So that would be 2 significant digits. I'm taking the log of that number, and I'm getting a negative 0.95. And then I'm adding that, right, to this number. So I have 2 digits after the decimal point, 2 digits after the decimal point, so 2 digits after the decimal point. So I'm back up to the 3 significant digits again. So again, just please pay attention to those. All right, so that's part A. Part B, half equivalence points. That one's pretty easy, right? We had said that our pH is equal to our pKa at our half equivalence point, so my pH is equal to 3.46. And really that's all we have to do. If I gave you a volume, right, because I could word this a couple different ways. Here I actually said halfway to the equivalence point, but I could have said after 50 milliliters of sodium hydroxide was added, and then we would recognize that that's the half equivalence point because I need 100 milliliters to get there, right? So if I had 50, I would be halfway to it. Anytime you're at the half equivalence point, your pH is going to equal your pKa. So that one was pretty straightforward. C is at the equivalence point, and we've already said that at the equivalence point, we're going to have, right, 50, where am I? Here it is, 100 millimoles of hydrofluoric acid, sorry, 10, I can count, 10.0 millimoles of hydrofluoric acid. We're also going to have 10.0 millimoles of sodium hydroxide, right? Because they're equal at the equivalence point. So let's write that reaction. I have hydrofluoric acid plus my base going to water plus sodium fluoride, but we're not including sodium. We have 10 millimoles. We have 10 millimoles. It's actually just 10.0, isn't it? I'm just double checking my significant digits here. Yeah. And then 0. And then remember, we subtract the smaller from the bigger. They're both 10. Add that to the other side. So at our equivalence point, right, my acid and my base have neutralized each other. They both go to 0. And then what I have is 10 millimoles of my salt, right? And the anion of the salt from a weak acid, strong base neutralization reaction is basic. So what I have here is a weak base solution. So at the equivalence point of a weak acid, strong base titration problem, it will always be a weak base solution, right? My salt from that neutralization reaction is basic. We do need to convert that to concentration. So my concentration of fluoride ions, I have 10 millimoles. And then my total volume at this point, right, if we go back up, I have 50 milliliters of hydrofluoric acid, right? That's what's in my Erlenmeyer flask. And then this number we calculated, we've added 100 milliliters of base to it. So my total volume is 150 milliliters. And it does need to be in scientific notation, right? If I take my 100, I have nothing after the decimal point. I add the 50.00 to it. I want 150 with nothing after the decimal point. This isn't my final answer, so I'm just gonna write it as 150, and I'm gonna underline that 0 to just remind myself that I want 3 significant digits. It's not my final answer. If I was to submit one, if this was my answer, I would have to put it in scientific notation. I can't just leave it like this. That's not an official way to write it. With that, it looks like a 6. This isn't an acceptable way to, write my answer. It's just because this is part of my work, I'm just using that to keep track of it. So it's okay. Just make sure that when you're done, you're going to write your numbers properly. So I have 10, I'm grabbing my calculator, divided by 150. And I have 0.0667 molar. Again, I want those 3 significant digits, right? 3 here, because I am counting that 0. So now that we have that number, right, we need to write our base dissociation equilibrium equation. I am going to need my Kb, so let's just calculate that right away. Kb is going to be equal to Kw, so 1.0 times 10 to the negative 14th, divided by my Ka, which was 3.5 times 10 to the negative 4th. I'm pretty sure, I just want to double check that. Yep. So I'm typing that into my calculator. And I get my Kb to be 2.9 times 10 to the negative 11th. So we would write our base dissociation equilibrium equation. We would set up our ice table. We would plug those into my Kb expression. And I'm going to shortcut this part a little bit. I am going to write my expression. So plus water going to hydroxide ions plus the conjugate acid. Right, and then we would plug our numbers in. So my concentration, 0.0667 molar, doesn't have one, 0 and 0. We would then do the minus x. I guess we'll do the whole thing. I was going to shortcut it, and now I'm not. Plus x. These are both x. And then this is 0.0667 minus x, though I am going to ignore that minus x because my Kb is small. We then plug those right into our Kb expression. So on the top, right, we have the concentration of hydroxide ions, which is X, multiplied by the concentration of hydrofluoric acid, which is X, so X squared. And then on the bottom, again, we're using that assumption that we can do when K is small. Solving for X, which we do want to remember equals my hydroxide ion concentration. And I get 1.4 times 10 to the negative 6 molar. And then I am just going to double check my calculation here real quick. Yep, I got the same thing. And then we do want the pH, so you can do this again a couple different ways. We can calculate our POH and then subtract it from 14, which is how I'm going to do it. Or you can divide your hydroxide ion concentration into Kw to get hydronium ion concentration. So for my POH, I get 5.86. Again, I'm not rounding after each step. I actually, instead of using 1.4 times 10 to the negative 6, I had the whole number still in my calculator. So 1.390, so on. So if yours is coming out a little bit different, that's why. And subtracting that from 14.00, I get a pH of 8.14, which is a basic pH, so we're feeling pretty confident in that, right? If it would have come out acidic, we goofed up somewhere, right? Remember the pH at the equivalence point for a weak acid strong base titration problem is going to be basic, right? And that should be hopefully somewhat obvious when we look at our neutralization table, right? This is 0, this is 0, and I have a weak base solution. We're expecting a basic pH. Okay, one more part. So I have to go find it. So part D, we're adding 130 milliliters of our 0.1 molar sodium hydroxide. So I'm going to determine or calculate the number of millimoles of base that we have. So I'm taking its volume, multiplying by its concentration, which I guess we probably could have done without the calculator. So 13.0 millimoles of sodium hydroxide added. And then again, anytime, right, we're adding acid or base to our acid or vice versa, we are going to write that neutralization reaction. So my equation for that, my hydrofluoric acid reacts with my base to produce water. And then again, the sodium fluoride, but I don't care about the sodium, so fluoride ions. We started out with 10 millimoles of hydrofluoric acid, right? Going way, way back up. 10 millimoles. I've added 13 millimoles of base, right? That's the number we just calculated. Subtract the smaller of the two numbers, which is 10. Add it to the other side. So my acid goes to 0, which we expect, right? At the equivalence point, we've neutralized all of that acid and we're still adding base. So at this point, I have excess strong base. So 3 millimoles. Here I do have 10 millimoles of weak base. That 10 millimoles of my weak base does contribute. It does produce hydroxide ions, right? If we go back up to this equation we just wrote, right? Those fluoride ions do react with water to produce hydroxide. It's just that if we did that and solve for this number, it's actually going to be negligible compared to this. So we can actually ignore it. So what I have is a strong base solution. So we need to convert that to concentration. So my total volume at this point, we started out with 50 milliliters. I've added 130 milliliters to it. So I have 180 milliliters right now. And then I'm going to divide 3 by that. And my concentration of hydroxide ions is 0.017 molar. And then I'm going to calculate the pOH and then subtract from 14. You could do it differently if you want. So I have a pOH, of 1.77. So a pH of 12.23. So just looking kind of back through it again here, right? Remember at the equivalence point, that's where my millimoles or moles of acid are equal to my base. So anything before that equivalence point is going to have excess acid, right? Because I've not neutralized it yet. So if we look at our tables here, I have excess acid. At the half equivalence point, if I was to write my neutralization reaction, I would have excess acid. You also have your conjugate base, right? Or the anion from the salt that we're producing is probably the better way to say it. And we would have that for both of these. So everything between initial, right? Once we start adding base to it, and the equivalence point is always going to be a buffer solution. At the equivalence point for a weak acid strong base titration, it's always going to be a basic solution. And then after that equivalence point, we keep adding strong base to it, right? We've neutralized our acid, but we're still adding strong base. So I'm always going to have excess strong base. I have another example for us. This one I already have written down. So same idea, please hit pause, write the problem down, work through the problem on your own, and then when you're done with that, hit play again so you can check your work. All right, so hopefully you guys did that. So this time I have 25 milliliters of a 0.150 molar hydrobromic acid solution, and we're titrating it with 0.250 potassium hydroxide. So this one is a strong acid, strong base titration, right? If I was to look at my hydrobromic acid, right? It is completely ionized because it's a strong acid. If we were to write our neutralization reaction for this and then get rid of our spectator ions, my bromine is actually going to get canceled out. And then remember that protons in water do bond to water, so I'm really going to think of HBr as being H3O+. When I write my neutralization equation, I'm just going to go right to my net equation, and that's how I'm going to write that. Potassium hydroxide, again, this is a strong base, completely dissociated. Potassium would be a spectator ion, it's inert, so it would get canceled when we write our equation. So I'm going to think of potassium hydroxide as just being hydroxide ions. So our first part, we're going to calculate the base needed to reach the volume of base needed to reach the equivalence point. So part A. Remember at the equivalence point, the number of moles or millimoles of HBr, so hydronium ions, is going to be equal to the number of moles or millimoles of potassium hydroxide, so OH minus. So we're going to first determine the number of millimoles. And again, if you prefer to use moles, that's fine. Just make sure you're converting your volumes from milliliters to liters. So 25 milliliters, 0.150 millimoles per milliliter. You could just leave it as a capital M, but I'm just going to write them out every once in a while so you can see it. right? Milliliters are going to cancel. And I'm grabbing my calculator here. And I have 3.75 millimoles of strong acid in that Erlenmeyer flask. We know at the equivalence point, my number of millimoles of base need to be the same. So I'm going to have 3.75 millimoles of hydroxide ions. We want the volume, so I'm going to divide that by its concentration, which is 0.250. And my millimoles again cancel. And we are going to be left with my volume. And I get 15.0 milliliters of potassium hydroxide needed to reach the equivalence point. So because this is a strong acid, strong base titration, after I add the 15.0 milliliters of potassium hydroxide, the pH of my solution is actually going to be 7. Part B, we want the initial pH. It's just a strong acid, so remember whatever your concentration of your strong acid is your concentration of hydronium ions, right? Completely dissociated. We already showed that up here, right? HBr, arrow going in one direction, hydronium ions. And that's 0.150 molar, so we can just take the negative log of that number to get my pH. And I got 0.824 for that number. So that's my pH. Right, significant digits, I have 3 here. Because this is a log value, only the digits after the decimal point are going to count. So 3 digits there, 3 significant digits. Part C, the pH after 10 milliliters of base have been added. So anytime you're adding base to your acid, we're going to want to write that neutralization equation and then set up our change table. I do need to know the number of millimoles of base that we've added. So I'm going to take that 10 milliliters of base. I'm going to multiply it by its concentration. Again, I'm looking at that molar as being millimoles over milliliter. And I'm going to get 2.50 millimoles of potassium hydroxide added. So writing our neutralization reaction, my strong acid reacts with my strong base. We're producing 2 water molecules. I have 3.75 millimoles of acid, right? That's the number we calculated up here. I have 2.50 millimoles of base. Remember, we always subtract the smaller of those 2 numbers from both of the reactants. So my base goes to 0. And I have 1.25 millimoles of my strong acid in excess. To get the pH then, we need the concentration. So we're going to take the number of millimoles and divide it by our total volume. So we started out with 25 milliliters, right? That's the amount of acid we have in our Erlenmeyer flask. And then we've added 10 milliliters from the burette to it. So we currently have 35 milliliters total volume. So 1.25 divided by 35, I get 0.0357 molar. And then just the negative log of that number. And that will give me my pH. And again, I'm keeping the whole number in my calculator when I do this. So if you're actually retyping in the 0.0357, you might come off a little bit different. So I got 1.447 for my pH. Again, watch your significant figures, right? I have 3 significant digits here. Only the ones after that decimal point count. So 3 significant digits. And then one more part for us, part D. Going back up to part D, 20 milliliters of my base. So same process. I'm going to figure out the number of millimoles of base that we've added. I'm going to write my neutralization table or my neutralization equation and set up my change table. So my acid plus my base, going to my 2 waters. We started out with 3.75 millimoles. We've added 5 millimoles of base. Again, subtract the smaller from both of them. So this time, all of my acid has been neutralized, right? That's going to go to 0. And I'm going to have excess base left over. Turning that into concentration by dividing through by the total volume. So we started out with 25 milliliters. So I'm just going back up to the problem, right? That's what we started out with. I've now added 20 milliliters to it. So my total volume at this point is 45 milliliters. And I get that my hydroxide ion concentration is 0.0278 molar. And then I do need the pH. I'm going to determine the pOH and subtract from 14, but as always, you can divide your hydroxide ion concentration into kW to get hydronium ion concentration, and then take the negative log of that number if you prefer. So I got a pOH of 0.556, and then I'm going to subtract that from 14 to get my pH. So 12.444. I guess just 44. So it's 14.0, just looking at sig figs that we're subtracting that from. So I have 2 after the decimal point, 3 after the decimal point. So I do just have 2 after my decimal point here. So as always, just pay attention to those significant digits.